Welcome everyone to this Agri-Tech Meets Navigation event this afternoon. We've got a really interesting group of people here today. So some of you are from the Agri-TechE membership and some of you are from the Royal Institute of Navigation membership. So it's a bit of a different group for us today, which is exactly the point of this event. So as I said, if you'd like to introduce yourself in the chat, that would be really brilliant because you're all well, lots of different people on the group, and I'm sure some of you have the interest in agriculture and some of you have the interest in the navigation side. So it would just be really interesting to know who you are, what you do, why you're here. So this is our first Agri-Tech Meets event. So thank you for coming on the journey with us today. And it's really come out of conversations we were having, particularly with technologists, but not exclusively, who have technologies in all kinds of different industries that think they might be able to do something in agriculture, but we're not quite sure where those sort of crossovers are. So we're hoping to bring together a bit of conversation, get some thoughts going, and just see what the potential is. You know, in agriculture, for example, we might be using these navigation technologies, but might not understand the full potential of them. I mean, I certainly don't. And on the other side, you might have those technologies in navigation, kind of spot those opportunities we have to make the most of it in agriculture. So the thinking behind the Meet series is to really bring those kind of people together and just see if there's opportunities for us to get together. So I am Becky Dodds. I'm the Director of Communities here at Agri-TechE, and we are a membership organisation. We work with farmers, technology, research and business support to get innovation out into the field, as I like to say. And technologies might include anything from sensors and robots to novel chemistry, or just pretty much everything in between, new rotations, new crops, all kinds of things like that. So it's really quite broad. And through our network, we run events like this. We run some in-person events, all kinds of different topics. We do profile raising for our members, and we make those connections that our members might be looking for as well, both in and out of agriculture. So the format today, we have 3 speakers. I think you're really in for a treat today, actually. I think we've got some nice speakers. They're going to introduce PNT for people who obviously are a bit more new to it, and we're also going to cover the agriculture side for those people that are on the technology side and want to learn a bit more about where we've been with PNT and where we're going with it as well in the future. There will be time for sort of points of clarification after each speaker, and then we've got loads of time for Q&A at the end. So feel free to ask questions as you go, or you can save them to the end and we'll do it in Q&A. So up to you, really. And I think with that, I'm going to hand straight over to Alex, who is also representing the Royal Institute of Navigation today, who we've partnered with on the event. So over to you, Alex.
Brilliant. I'm just checking if I'm sharing my screen before I start talking.
Yeah.
Cool.
Looks great.
I need to move mine. So hello, I am Alex. I am the RIN representative here today. So I'm going to give a bit of a crash course onto the RIN itself, what PNT is, and try and tailor this towards more of an agricultural setting. So I am with the RIN, I am on their PNT advisory board and I run their early career network. Whilst also I'm an Agri-TechE member through the University of Warwick, where I'm doing my PhD in an agricultural sense as well. Hence why I've got my Agri-Tech facility picture up on the background. But jumping into what is the RIN, making sure I can get this. So first of all, the RIN is a learned society founded in 1946, and we have a variety of different special interest groups ranging from maritime, aviation, we even have animal navigation, and of course, probably what's interesting to us to hear today is PNT. We have the bold vision to be the go-to inclusive group spanning diverse disciplines, all working together for a more navigable world. And we have membership associations spanning over 60 countries across all continents. And back here at home, we are deeply involved with the UK PNT's office and advise them on PNT resilience and best practice. And here's a good one to check out if you're ever interested in PNT itself. Some of the sources we'll discuss. They host a lot of events to check out. And if you're so inclined, you can come to my early career conference or send someone their way. But jumping into what is PNT, positioning, navigation, and timing. Now, interestingly, when you talk to anyone working in PNT specifically, you often find out they forget the navigation time. because the view tends to be is positioning and timing enable navigation. If you have your position on a coordinate framework over a certain amount of time stamps, you can work out where you're going, you can work out your speed, acceleration, and it all feeds into that. But what are our sources of PNT? And this is a very brief overview. There are many sources that I've not covered on here, but you have ones you'll know from GPS, your cell phone service, Wi-Fi, Bluetooth that you've probably come across. You have IMUs. We can fit them down into smartphones and cost pennies to having very expensive £1 million ones and subs. And we even have quantum up and coming going on. And then we have perception, which we'll probably be using in robotics, camera, LiDAR. You can start using odometry with them and make them a source of PNT. Now, all of these will have different pros and cons of when and why you would use them. And often we like to preach that not one is to fit all, but you often find GNSS tends to be seen as the primary source of PNT. So what is GNSS? Global navigation satellite systems. You would definitely have heard of GPS before. The American systems, the Europeans have Galileo, the Russians have GLONASS, the Chinese have Beidou. These are all different constellations that form GNSS when we talk about it. And it tends to be the primary source, especially when you're outside, because it works extremely well outside when you have a clear view to the sky. And also it gives you this global coordinate. Many other systems, they will say where you are in the local map, which can be helpful for what you're working. But when you need to know where you are on the Earth, GNSS tends to do well for that. And it's growing in agriculture. In 2012, about 200 GNSS devices were shipped out into 200,000 GNSS devices were shipped out annually to the globe. And in 22, that's grown to 1.3 million annually shipped out to agricultural services. And that's yet to grow. And when we look at the revenue for GNSS devices and services, the European Market Report has predicted in 2033, this will be over 23 billion euros worth, with a lot of the growth coming from commercial augmentation services. And when I say that, what do I mean? This comes down to the correction services you've probably come across. If you take your GNSS receiver, you often find, yes, it's accurate, but it's not that accurate unless you have one of these services. You're probably, in a modern receiver, going to get just under 2 meters on a good day. But for many of your robotic applications, you probably want centimeter level. You often see 2.5 centimeters quoted, because that is precision agriculture for the American market. And unfortunately for GNSS, you have a lot of these inherent errors that you're going to get wherever you are in the world. And that comes down from the satellite's clock error. It might be ever so slightly off. The orbital error, its position where the satellite says it is, might be ever so off. The atmosphere causes some issues. If you're not on a dual frequency receiver, a single frequency, the atmosphere error can be between 5 to 10 meters. But these are inherent and these can be calculated. There are ways we calculate them. One of these ways, or the two you will know, is RTK, real-time kinematics, and PPP, precise point positioning. RTK is essentially where you have a GPS base station, a GNSS base station, usually requiring a good antenna. When it comes to these things, a good antenna is key for base stations. And you can calculate what these errors are and pass these corrections on to your robotics, your roving GNSS receiver, and you can bring your position down to about centimeter level accuracy. Where PPP, you don't require a base station. These are global corrections, usually passed on through the internet, through your cell SIM card if you've got service. Starfire famously use their satellite constellation to provide these corrections, and you don't need a base station to do these. There are some pros and cons to both, being the infrastructure and the time to converge. And what a lot of these services have now kind of come up to sell you is this hybrid in between PPP RTK, where they provide these PPP corrections and they use base stations across the country to kind of provide these corrections instantly, and it's extremely effective. Thanks so much. We've got different grades of receivers that you might be wanting to use when you're working in agriculture. And we have the very high end. These are very robust receivers worth tens of thousands. And you'll probably be paying £500 to £800 a year for your correction services. And you get millimetre to centimetre level accuracy depending on the conditions. And you'll probably find previously, for tractors to have auto steer, they would have had some of the higher end materials costing quite a fair bit. But they have been breaking through. RTK correction services have been effective at lower cost prices. And now you can buy this hardware from agriculture specific manufacturers for a couple of thousand. Yet again, you're paying for that subscription fee. You can get some baseline ones that will bring you down to tens of centimeters for free. And then, of course, you have the license fees, which probably causes farmers many grief to navigate. And then we come down to the mass market dual band modules. As I say, very important to have dual frequency in these receivers. And they cost a couple of hundred. And also the subscription fees are a lot less, £60 to £400 a year. I've seen you can pay £5 a month and get about 100 hours of usage. So they're bringing it down to the everybody kind of scale. And what a lot of robotic companies have also started doing is selling their own base station, so you don't even need the subscription. And these can come down to about 3 to 6 centimeters as well in good conditions. Now, looking at this, you might see the mass market, it's pretty affordable. And you may think job done. And in fact, if you are testing out in an open field, you'll probably feel like it is job done. But unfortunately, as you go down lower in price, the robustness starts to fail. And there are many other sources of error to GNSS. Not to be alarmist straight away, but you start to have GPS jamming coming from conflict zones. If you're in a border state, they can overspill. But also, solar storms are a very rare occurrence, have been known to cause GNSS, even with RTK corrections, to shift their position off, previously causing issues affecting auto steer. If you're working on a cheaper receiver, you'll definitely feel it if you've got vegetation obstruction, be it trees or your robotics underneath the corn or wherever you're working. These receivers work with line of sight to the satellites. So as long as you can see the sky clearly and nothing's obstructing them, they should be okay. When you have a cheaper receiver, the more obstruction, the less robust they are, the more they're going to be effective. And then this brings me on to the research that I'm carrying out is covered agricultural structures, where they have these clear coverings on them, but the problem is it's the metal framework causing the issue. And what you'll find with these is the signals will bounce off the metal and cause, I think, a phenomenon called multipath, which distorts the signal and causes a lot of error to deal with. When it comes to greenhouses, you have a lot more metal frame to hold up the glass, and you're probably likely to know where you are in a greenhouse being the north, middle, or south side of it, and area-based. With polytunnels, they're not too bad. There's a lot less material in it. And what I'm hoping to do with my research is to work out how you can mitigate some of this multipath to bring it back down to centimeter level accuracy. But with all these errors coming in, if you're working on a lower cost one, you want to start then bringing in other sources of PNT if you're not working in an ideal situation. And that was very much my crash course into PNT, tailoring it towards agriculture. But I will give out another shout out to the RIN. Please give them a look if you're interested in PNT, especially some of the sources more in depth. And if you're working on polytunnels and GNSS and you want to continue the conversation, do give me a shout as well. Thank you very much.
Brilliant. Thank you very much, Alex. And I guess you're already starting to bring out some of those sort of specific challenges in agriculture, like the metal framework. I guess you wouldn't instantly think, oh, this is going to be a problem. And oh, turns out it is. So
yeah,
unless anyone, oh, sorry.
Sorry, I was going to say, yeah, it's good you bring it up, and to highlight comes down to the mass market one, because you can solve some of these problems by sticking a 20 grand antenna. But obviously that's no use to many people trying to build something. So yeah.
I was just going to say, if anyone's got a specific question, if you want to drop it in the chat, I can ask it before we move to Kit, but I will ask one of my own otherwise. So I think it's quite fair to say you're a little bit newer to agriculture. It's not particularly where you came from. Is there anything that's really surprised you when you've started working in agriculture, or something you thought, oh, I've never really thought about this before? And yeah, just a surprise, really.
I think the surprise is actually agriculture is one of the early adopters in many ways when you look at auto steer on tractors, and they really hammered that home in the high quality one. And it's how some of the smaller robotics are taking it on, because previously you could spend tens of thousands for an antenna, and now you can build them for 100 odd, and it's building them on, and how some of these companies are taking them on, how they're selling off base stations and innovating around how the market sort of brought these prices down has been pretty impressive.
I will take that. It's not often we're called early adopters, so I think that's going out on LinkedIn, that one. Brilliant. Thank you very much, Alex. And he'll obviously be here again for the Q&A. In the meantime, I'm going to pass over to Kit. So while we've all just had our lovely lunches, it's a little bit of an early start for Kit, but take it away and you can tell us a little bit about the agriculture lens on PNT, please.
Yeah, yeah. Good morning / afternoon, everybody. Yeah, so I'm Kit Franklin. I'm a senior engagement fellow at Harper Adams normally, although currently I'm in Mississippi State University as a visiting scholar. I work on ag automation and robotics, and generally I'm an agricultural engineer. I was put up to this by the IAGRI, the Institution of Agricultural Engineers, of which I am the president-elect. And oh, if I can get a thing to move, here we go. I just therefore thought I'd plug the IAGRI. So the IAGRI is the Institute of Agricultural Engineers, a professional membership organisation for all those working or with an interest in engineering, science and technology within ag and the environment. So yeah, if you're working in agriculture as a professional and you're doing engineering, tech and science application to ag, we'd love to hear from you and love to have you as part of our membership. So there you go, plug over. So again, I think we've heard maybe a chunk of the start of my talk, but I will go over it quickly just to try and to try and pick up on some extra things. So critically for me, the way in which GNSS, or what we all call GPS, sort of works critically is through trilateration. This thing I always talk about with my students because people assume it's triangulation, but it has nothing to do with angles and it has all to do with distances. And the clock pulses that Alex were talking about that travel from space, ultimately we use those clock pulses to determine a time of flight for how, and that time of flight can then determine how far away we are from a satellite. And by knowing how far we are away from multiple satellites is where we can position ourselves. Now, each of these satellites, in the case of GPS, broadcast multiple bands, and that becomes important later. So as Alex has already said, there's multiple different constellations. The US system GPS coming first, followed by GLONASS, and then Galileo and Beidou later in the 2000s. And as I say, they're in an orbit that allows them to orbit in around about 12 hours, give or take, and they all work in very similar ways. And this is important to us because as people trying to get precision from our global navigation satellite systems, we can use those multiple signals to improve things for us. And critically, the errors that come from GNSS are from refracted signals. So signals that have been bent and warped, and in Alex's case is bounced off of a glasshouse framework. And those bouncing and warping of those signals essentially exaggerates or extends the time of flight that it would truly take to make the same path to get from the satellite to the user. And those extended paths create inaccuracies. But if we use multiple carrier signals from one given satellite, they are refracted in different levels, and therefore by using multiple carrier signals within our GPS chips, our GNSS chips, we can improve our accuracy. And ultimately, by connecting to more satellites and more signals and more constellations, so with modern chips, you can talk to all of the providers in one chip. that will always improve your signal. And the reason I say any of that is because, again, I often have conversations with farmers who kind of say, well, how can you buy a GPS for walking that costs a couple of £100, whereas I'm buying an ag-related machine and it's costing me thousands? And ultimately, it's just because the tech is better. The tech is talking to more satellites, more signals, and crunching more numbers to account for this warping and refraction of the signals. So differential GNSS, Alex has already covered. We're using base stations on Earth and known locations to calculate the error of the GPS signal, the GNSS signal at any given time. So I like to do this if I'm on a lecture stage by doing a little interpretive dance. So if I know exactly where I am and I've not moved and I'm calculating continually the GNSS position, I can essentially calculate the error of that calculation at any given time, and then I can broadcast that to a machine in the field. We can do this regionally, as Alex was talking about. One of those systems that certainly was talked about in ag 15 years ago a lot was EGNOS. Can I get an EGNOS signal, which was a whole European-wide signal? Now, the problem with the European-wide signal is the correction was being calculated maybe quite a long way from where you are. In the UK, there was 2 correction stations, one in London, one in Edinburgh or Glasgow. My mind slips. But, you know, if I was sat in Harper Adams in Shropshire, those signals aren't going to be entirely relevant to me, and therefore the correction was only so good. So RTK comes in. RTK, this sort of very localized correction, comes in. Now, the image down here at the bottom summarizes how that may look a lot of the time. Down at the bottom right, where again 20 years ago you might have had your own tripod out in the field with an RTK base, and that would give you repeatable accuracy. Now, this is a really critical thing. So there's one thing with pass-to-pass accuracy, i.e. I can drive down the field and drive back 10 minutes later or a few minutes later, and I'll be pass-to-pass accurate of a few centimeters. But that doesn't mean, and that's the sort of accuracy you get using EGNOS or a regional correction. But the problem is, if you come back to that field a month later, 2 months later, those signals will not be repeatable, and you could be offset by, again, half a meter or so. So if you've put a bed of potatoes in your field and with a regional correction, you come back a couple of months later, you could essentially drive down your field, and rather than driving down the wheelway, you would drive straight over your potatoes. So that's not ideal. What you get with RTK, with this highly localized base that you tended to own as a farmer traditionally, is you would get full repeatability. So you can put a 20p piece on the floor and you can come back 6 months later and you will find that 20p piece exactly where you left it. Now, you can then do this via subscription models, as again, Alex described. One of them, this sort of N-trip model, which is a cellular based, so you get it via a cell signal. And there's companies like RTK-Net in the UK who have been really great at getting cell-based correction all over the whole country. So you don't have to own your own equipment anymore, you just pay that subscription. Okay, so why do we want it in ag? Well, we're facing some challenges. We're facing a reducing rural labour force. The graph on the left shows you that over the last 100 years, we've got a fifth as many people working on our farms. We've gone from 2.5 million to 500,000 people working on our farms, which represents just 1% of our population now. As population's grown, the amount of people working on farms has reduced. So we've got farmers trying to cover more and more ground per person than they did before, and we have a growing population to feed in the background. We also have the climate change agenda, and we are trying to meet net zero as agriculturalists. And as well as trying to meet net zero on our farms, we're also at the front edge of facing climate change as well. So we face it and we're having to meet it. So, and what I mean by face is we're the ones that get hit by floods and droughts and all the rest of it. And we're also the ones, and what I mean by meeting it is we're the ones that are being expected to draw down carbon and all those things as well. So precision ag is how we're going to try and get, or is one of the ways we're going to try and get there. We're going to basically observe our fields and break them down into sub fields and sub areas of our fields and try and treat our plants as individuals and do the right thing at the right time in the right place in the right way. But you can only do the right thing at the right time in the right place in the right way if you know where you are. So GNSS is absolutely critical for this idea of precision farming, treating plants as individuals and being very wise and minimal with the inputs we put into our farming. We don't want to waste chemicals and waste fertilizer. We want to be very targeted with it. So as I say, so the first thing we can use GNSS for is essentially as a data reference to hold our information around our field. So the top left diagram is showing a device for doing a thing called electronic conductivity testing, and conductivity of soils can essentially help you understand the soil characteristics across a field. So as you drive one of these machines across a field, you'll be picking up the conductivity and you'll be referencing that to a GPS coordinate. And then we can view that later as a map. Another thing we might want to geo-reference would be something like an NDVI reading. So an NDVI reading would be where you take a camera, maybe on a satellite, maybe on a drone, maybe hung from the side of a tractor cab, and you would drive that camera or fly that camera over your field, and you would use the reflection of different bands of light, so near infrared and red, to determine the health of your crop in any given location. But once you've determined that, you want to tie that to that location so you can start understanding how your field looks and understanding how to interact with your field in a more precise way, in a more targeted way. So data referencing is first and foremost what GNSS is useful for ag. What we might also want to do is drive our tractors in nice straight lines. And why would we want to do that? Well, we don't want to have misses in our field. We only have one field, or one area of land that we're farming. We don't want to miss opportunity by driving in wobbly lines and having gaps in our fields. So one of the early ways in which GNSS helped this is providing a light bar, so a physical light in which the tractor driver could follow in order to maintain a straight run down the field. So this was still a manually driven tractor, but being guided by an electronic device telling them to drive in a straight line. Now, the image on the left is is a pretty early one of these, Centerline by T-Jet. This is a mid-2000s device. But this is still a product you can buy today, and Agri-Precision on the right-hand side is actually a British startup, a UK startup, been around for around 12 years, 10 or 12 years, something like that, selling a very basic system. It comes with a light bar and a GPS unit you mount on the bonnet of your tractor cab, but it also has an iPad app that you can run in the tractor cab as well that you see in the background. So although this very much manually guided system is quite basic, it is still on the market and is still making money for UK business and also being benefit to some UK farmers. Auto steer is the next step. So you take the driver out of that loop and you steer the tractor automatically. The image on the left-hand side is a nice traditional system where you're on a nice fairly flat field and the tractor can have one receiver and drive in straight lines and cover the whole field in a perfect stripy way. It also means you can drive more efficiently. You do a thing called skip runs is what you're seeing here, where the tractor's been up and down the field skipping rows so it doesn't have to turn really tightly on the headland, and then it can come back and fill in later. If you see on the right-hand side, this is a system on an aggressive side slope, and the implement actually has its own antenna, its own receiver, and by having its own receiver, the tractor essentially is driving off of the designated straight row that the planter wants to follow, but is essentially accounting for the fact that the planter is sliding down the hill. So again, you get what you pay for in these systems. And if you're paying for a system that can cope with this, there's been an awful lot of testing, an awful lot of development in the background to allow that sort of system to work. Savings by just adopting this and reducing your overlaps and reducing your misses in your field is in the order of 5 to 10% saving on wasted inputs. So not a negligible amount when you think of the hundreds of thousands that some farms spend on fertilizer and seed and things a year. Next step would be extrapolating our GPS from our tractor cab out to the implement in which we are towing. And by doing that, we can look at my very pixelated, horrible images here that I probably need to update. And we can turn on and off outlets from a sprayer boom or outlets from a seed drill to basically turn off every single nozzle or every coulter to prevent any overlap between our passes. Now, why is that important? Well, in a thing like, putting on a herbicide, that you may not want to spray an area in your field. You may have a no spray zone. If you're putting on a fertilizer, you may not want to double dose that fertilizer because it can cause crops to lodge and fall over where they essentially grow too aggressively and end up falling over. Again, the same can be said with duplicating of our seed. Now, so agronomically, it's not good to have overlap, but also financially, it's not good. And we can save another 5 to 10% of inputs with an auto sections shut-off system. And these systems have been available on the market for about 15 years now. Variable rate is the next thing we might want to do. So after we've been out, flown a drone or done some sort of way of understanding variation in our fields, we may want to actually physically change the dose of fertilizer we put into the field. So we may want to put more in some areas, less in other areas. Now, this tends to be limited by the width of a machine. So the whole boom can only be up, or the rate of a whole boom can only go up or down together. So you get this sort of striping effect as you go down the field, how you can deal with it. Now, in time, and there are some early adopters of sort of individual nozzle control where you would change every single outlet to be a perfect rate and get to this more granular pixel-based level. So this is still very, even though people have been talking about it for probably 15 years, and I think the product you see on the left-hand side is a nozzle body with 4 nozzles to allow 4 different rates to be sprayed. Reality is the uptake of this is still very early doors and not particularly common to get this sub-boom variable rate. Again, coming back to where can we hang data? We can hang data off of a GNSS coordinate, but yield mapping is a really critical thing for this. So where we take a harvester, in these images, a combine harvester for cereal crops, we take it into a field, we harvest the grain. As the grain is harvested, we then monitor the flow rate of that grain, and we can map that flow rate and that given yield to a position in the field. Now, there's lots to go wrong here. The crop is cut at the front of the combine harvester. It's housed at the back of on the back of the harvester after a multiple second delay between the 2 places as it travels through the machine. The GPS is on the cab of the machine. So calibrating and aligning your yield maps is a real tricky thing to get right. And again, something that people don't think about, but yeah, if you really want to know exactly where you've got high yields and low yields, calibration of these systems and where does the crop that goes through the sensor, where is that being logged, and is it being logged in the appropriate place is really important. Now, the width of your combine header directly impacts the precision in which you harvest. So you see these lovely marketing images like you see here in the bottom right-hand corner, which show a very, very sort of granular topographical map of yield. But the truth is that's actually a bit of a lie. And reality is you only get 1 yield position per width of your machine. So you actually end up with a barcode across your field. So as ever in life, don't always believe the hype. Don't always believe the marketing. So just to, for those not in an ag space, those in an ag space, I'm sure a lot of what I've said is stuff that everyone's comfortable with and knows about. But if you're in the ag space or not, it might be surprising to you how long this stuff's been going on. So the first variable rate controller was being tested and sort of rolled out early adoption in 1987. The first grain yield monitoring was happening in 1992. And actually, I should give a shout out to the current president of IAGRI, Mark Moore, who actually did his PhD in around 1992, all around yield mapping. So his whole PhD was on this subject. So you can tell I was the second up to be asked to give this presentation. He would have been far more expert than me. Auto guidance then came around in sort of 97. A company called Beeline, or a product called Beeline, brought that out. Automated spray controllers, 2006. And then we can jump across to a fully autonomous field crop production. And this is very much me giving myself a tap on the back, because this is what I'm known for, which is a project called the Hands-Free Hectare. In terms of apologies, these have been copied out of a paper, but in terms of uptake, and again, apologies, this is US data because I just can't find any on the UK right now. But if you look to sort of adoption levels The left-hand side one shows dealer access to technology. Now, a dealer in the USA is more like what we would call a contractor in the UK. So this is a service provider. And in 2017, there was 78% of dealers, or these sort of contractors really in the USA, had access to GNSS auto guidance on their machinery. So a really pretty good uptake at that point. If you look to areas actually utilizing GNSS, you can see that, again, in the US in sort of 2016, 2017, 60% of the maize in the whole country, the corn as they would call it here, that was planted with GNSS being used. So pretty big adoption. And again, these numbers are now pretty out of date. This is now 10 years old, even though I can remember this paper coming out and it doesn't seem that long ago. But anyway, pretty out of date data, but still uptake is fairly significant, fairly high on sort of commercial scale farms. And I would say that this is reflective of what is happening in the UK. The big tipping point, just what's in my mind, was at the point when rather than farmers have to adopt this technology themselves, i.e. go to a supplier, buy a GPS system and fit it to a tractor, the real turning point was probably around about 2010 when tractors started coming direct from factory with these systems being applied. And now, even if you're not a farmer who buys brand new machinery, if you're a farmer who buys machinery that's 5 years old, well, you're probably now, even if you only buy secondhand machinery, you are now likely to be getting your hands on tractors that were fitted with GNSS from the factory, because that's been sort of 10, 15 years since that became commonplace. So just to look at sort of full automation, and again, this is a scandalous plug for my own work. I apologize. I could have used images from John Deere or many other companies. But yeah, this is the hands-free hectare. This is work I did at Harper Adams, where we had a fully autonomous farming system. You can read about it in the paper at the bottom. Again, scandalous plug. But basically, this was in 2017 and 2018. We grew crops entirely autonomously using machines that were navigated by GNSS position. Now, what I should say is our machines, certainly in the first year, this is actually second year video that we're watching, in the first year, drove in very wobbly lines. And we had RTK. So we had 20 millimeter accuracy in terms of position. That does not mean that your tractor drives in a straight line or your robot drives in a straight line. There is a difference between having good position and having good control of your vehicle. So again, just say that. It still needs algorithms and still needs engineers to make those machines drive in straight lines. And ours in the first year certainly did not, despite having that highly accurate signal. If you look to other automation and reimagining the sort of form factors of ag, here's a thing called a farm droid, where they're utilizing GPS to navigate a solar-powered robot across a field, and this robot is planting crops, and it is also remembering where every single seed is located. It is geolocating every seed, and by geolocating every seed, it can come back and use that known location to weed between every plant that is being grown. Now, systems like this exist using cameras to guide the implement, but this one is actually using GNSS position to guide the implement. So yeah, GNSS has allowed us to think of new ways in which to farm, new outputs. You know, this is a slow, methodical machine that lives in the field. It uses solar power rather than diesel power, and all of that was enabled by GNSS. So it has allowed us to reimagine farming, and I'm sure Ben is going to talk a lot more about that. So thank you very much. This is the end of me talking, so I'll try and stop sharing my screen now. Again, another shameless plug. I've got a podcast if you want to hear me chat about all this stuff on a weekly basis. Thank you.
Thank you so much, Kit. And I'll allow the shameless plugs, partly because Hands-Free Hectare is one of my favourite projects of all time. Not that I have favourites, but if I did, it would definitely be that one.
Well, thank you very much.
I have got a question from Ben, actually. So as soon as our next speaker,
no,
I'll ask it.
He's going to throw me under the bus, isn't he?
No, he wants to know, can a fully autonomous farming system be financially viable?
Yeah, I think our economic modelling, which I didn't include in this because it seemed a little bit far out for this very specific talking point, Our modeling shows that it can be, but it is wholly reliant on that system being reliant, and reliable. So we need systems that, so our modeling all works on sort of 10% interaction with the farmer. So you go out to the field, you set the machine up, you press go, you walk away, you maybe come back at lunchtime, have a little monitor, or you monitor remotely. If you've got troublesome systems, like mine mostly were, and things get blocked and you have to go and rescue things, which definitely happened in our project, certainly our bigger and more ambitious hands-free farm that we did, that kills the economics very quickly. So you need reliable systems is what you need to make autonomous farming a reality. And yeah, I will talk about that all the time with engineers and companies and students I work with, that if you want this system to be successful, reliability is absolutely fundamental. Otherwise, it just won't get adopted and it will not change the economics of farming one bit.
And I guess kind of on the other side of that, it's up to all our businesses to have that plan B as well, that kind of fail safe, if you like, if we can, where possible.
Yeah, but I think the problem with farmers is they don't often give technologies much more than one chance. If you take it to the field and it doesn't work, it will soon find its way into the stinging nettles and the old machine will come out. And yeah, you don't get many chances to mess up with a farmer. So now that doesn't mean there's not really great farmers who are happy to work with developers and work. And again, Ben will have worked with many really great farmers who let him go and test and trial and develop machines on their farms. But when someone hands over that commercial money, you don't get many chances to get it right, and you need reliability.
Yeah, that's very true. And I'm sure Ben is about to tell us the same thing. And just a reminder, if you've got some questions, we've got a Q&A after. I've got some questions if you haven't got them. But thank you very much, Kit.
No worries.
Oh, I think one more question just came up there, Becky.
I'll come back to it. I will come back to it.
Do you want me to kick off?
Yeah, go for it. Yeah.
Excellent. It's got to be said that the work that it can't be overstated that how important the work that Kit did around Hands-Free Hectare to influence an entire generation of agri-tech entrepreneurs, of which myself and my partner Sam were included. Yeah, I think he underplayed that quite massively. And also recently saw James Lowenberg de Boer talking about the financial viability, and admittedly reliability is definitely one of those things, but I think it's incredibly interesting that the standard view of farmers, certainly across the North America and Europe about bigger is better is not necessarily true, and I think it's an interesting thing that will move and develop. My name is Ben Scott Robinson. I am a serial entrepreneur, I guess you'd say. But my initial engagement with RIN was when I was working at Ordnance Survey. I was lucky enough to be there as the head of experience and then running all their sort of experience design, and actually had control and looking after the maps for Ordnance Survey, which was very exciting. And my first sort of brutal introduction, I suppose, to the power and vagaries of GPS and particularly RTK was through a project that I arrived that was halfway done at Ordnance Survey, which was a little app they developed called OS Locate. The idea being that sometimes if you are completely lost up the side of Ben Nevis and it's incredibly foggy and you've no idea where you are, you just need to have a location, and a location which is reliable and a location that relates to OS maps, because obviously OS maps are the best for that sort of situation. And what we found was no matter what we did, there was always this huge vagary, and that then introduced me to RTK, and then introduced me to the fact that Ordnance Survey also owned the system called AusNet, which is the network across the UK of geolocated base stations, which certainly at the time, and I believe still is the fundamental basis for a lot of RTK services, in that You have to cross-reference your GPS reference with the AusNet base stations to make sure that you can find out exactly where you are. The journey at OS, I'll just sort of quickly expand a little bit more, also included work looking at off-road routing. And that was particularly interesting because it wasn't really an area that seemed to be explored that much. Firstly with OS Maps, which is a leisure mapping app, which is, I believe, extremely popular now, which is very reassuring. But the focus of that was, you know, if you are walking or mountain biking or just generally sort of wandering off the beaten path, Ordnance Survey maps are what you rely on and trust, as we'll come on to in a bit. But if you are using your phone, which obviously many people do, then you needed an equivalent, and that's what we were looking to provide, and then increasing the capability by introducing the routing, which meant that you didn't fall off the side of a cliff and you could walk safely through the countryside without any problems. Apologies. So then that followed up with a project that we did for the Cabinet Office called Resilience Direct. No, I haven't moved, sorry, James. So did a project with Resilience Direct, Cabinet Office called Resilience Direct, which was focused on providing the information for emergencies, for emergency services when everything goes wrong, and was used in Cobra a lot. And the really exciting thing there was, for example, being able to provide routing and location for emergency services, which changed if flood levels rose. So if roads were flooded or bridges were taken out, then routing was changed accordingly. And that became incredibly successful. There were a couple of floods at the time where the emergency services that were using Resilience Direct mapping rather than the sort of the systems they were normally using managed to get to where they wanted to go on average, I think about 20 to 30 times faster. Percent faster. So it was very interesting to work with navigation, location in this way, which is very different, I suppose, to the sort of standard view of it. But I wanted to...
Ben, sorry to interrupt. We can see your first slide. Is it correct? Okay.
Yeah, sorry, that was a little spiel, sorry. Just quickly cracking on. And sort of picking up on a lot of the stuff that Kit was talking about, sort of navigation particularly and location for most farmers involves the navigation of their vehicles, their tractors, through the field. The line, if you like, the line that those vehicles follow, and the clever ways in which they manage to do that. And ultimately, the purpose of this sort of navigation system is that they cover 100% of the field. There's no gaps, they don't overlap, they're not wasting chemicals, in inverted commas, and they're not leaving patches where those chemicals aren't being used. And it is absolutely key and very important, and has become an absolute staple for farmers for a long time. But what I want to explore, I suppose, a bit more is on this interface you can see here, what is the grey bit? And Kit sort of touched on this, and I think that I wanted to delve a bit more into this to understand the importance, particularly of location, and location and context, and what it can mean for farming. So as anybody who knows Ordnance Survey maps will know, that the line is relevant if you are trying to find your way from A to B, but in many cases the context around that line is incredibly important. And this was actually an example that was used when we launched OS Map at Ambleside at the outdoor show, showing the difference between what you would get from generally considered to be the world's most used mapping system, Google, compared to Ordnance Survey. Now, if you look at Google's map, what you see is Ambleside is in a green area because it's in a national park, and so they make everything green there, and it's next to a blue bit, which is water. And there are some nice places to stay, and there's a few roads. But the reality of the area around Ambleside is that it's hugely craggy, mountainous, a fascinating and beautiful place to walk, but also potentially very dangerous. And so when you are looking for a way to guide yourself safely through this environment, you don't just need the line, you need the context. And the reality is that, you know, if you are not using that context in this place, it could be very dangerous for you. And the context in farming is really around what is in the field, because a field really isn't homogeneous. Despite the efforts of the last sort of 80 years of farming to produce a field of wheat or corn which is completely uniformly spread across the field with no gaps, the reality is that plants aren't uniform. They're plants. They're natural. Even though they're carefully controlled and in many cases sort of developed in a lab, they still come out slightly different, and they still grow different ways depending where they are in the field. But most farming equipment at the moment still assumes that this uniformity is the norm, and as a result, you have a huge amount of wastage. So, for example, the work that my previous company, you know, we found that up to 30% of fertilizer was completely unnecessary, not because it was necessarily being over-applied, but because it was being sprayed in places in mud where there were no plants at all. So therefore, you know, people were wondering, where is this extra 30%? Where's this runoff of fertilizer coming from? Why do we suffer from these massive algal blooms caused by phosphates and nitrates running into the water when, you know, we're applying as little as we feasibly can? It's because it's being applied directly onto mud, which then gets washed away, which is both tragic from the perspective of the farmers in that they're wasting money, and generally in terms of the environment, both on land and at sea. And then from a herbicide perspective, this is an oft-used fact, but something that we were lucky enough to be able to prove. When you apply herbicide into a field, and I'm going to use cereals here because it's what I know best, the first application that you apply, there's quite often quite a few weeds in the field because the crop plants haven't emerged yet. But later on in the season, when you have only a few weeds, you know, maybe 1 per meter squared, maybe less, because the previous herbicide was so effective, there's no need to spray the whole lot. And there's a huge amount of wastage. Up to 90% is something that we saw on a regular basis. 97% was the worst we saw. Also, when you're applying selective herbicides, although they don't kill the crop plant, they do in many cases stunt the crop plant a bit as well. So by applying the herbicide to make sure the crop plant can grow, you're actually in a position where you are stunting the crop plant at the same time. So, you know, in this case, it's pretty obvious that being able to understand context and location in a field becomes extremely important. And the way that this has tended to be viewed and solved with existing systems is an immediate sort of view and respond system attached to spray booms. So John Deere have put an awful lot of work into a system called See and Spray, which was based on an earlier development of a company whose name has completely gone out of my head. But the system was aimed to be able to see where weeds are and then just spray those weeds, which is terrific, which gets rid of a lot of the waste that we're talking about and allows for less damage to the crop plants and general pollution. But is this an ideal solution? Because this isn't really understanding this isn't really taking the context of the field, literally react to what you see directly in front. Wearing blinkers walking down the road. You know, you can make sure you don't bump into a wall or step out in front of traffic, but doesn't necessarily give you a huge amount of clarity in what's happening around you. And the reality is that, you know, that fields are hugely complex. Nature is hugely complex. They are made up of a huge amount of context. You know, if you don't see the field, if you don't understand the way the field is reacting to the crop plants, if you don't understand the historical nature of what's happened in that field, if you don't understand how that field reacts to rain or drought, if you don't understand the shape and topography of the field, then you are missing out on being able to understand how to maximize the crops that you're growing, but also minimize the amount of inputs and potentially damage that you're causing in those environments. So, a field is made up of, yes, obviously the soil. And as Kit was talking about before with conductivity, you can understand the makeup and the consistency of the soil, as well as the amount of water that's within it. It's made up of the crop, which obviously covers the vast majority of the field, but also the topography. In my previous company, we found that there were a huge difference between the size and the yield from crops, whether they were sitting on the top or the lip of a ridge, or whether they were in a dip or a gully. Just because water drains away from that top ridge, so it tends to be drier, and crops don't like that, and it tends to settle in the gullies, which means that those crops tend to be waterlogged, and they don't like that either. The weeds, they're not uniform. They react to there tends to be an imbalance in the soil quite often. It reacts to what was there previously, and can often just be a reflection of the history of the farm itself. And then the way nutrients apply, there's an assumption that the soil is just one big sponge that absorbs the nutrients evenly when you spray it onto them, so that it can then is readily available for crop plants. But if you're dealing with sandy soils, then these nutrients will drain away. Or if you're dealing with sort of clay soils, then they will sit on the top rather than going into the soil themselves, being nice thick soil with difficult to absorb things. And then obviously weather. Weather is, despite everything that has been done in agri-tech and advances with robotics and AI and all the rest of it in this industry, weather is the biggest influencer. You can't, it doesn't matter how much you understand the field or know what's going on or reduce the cost of the units that are out there. If the field is waterlogged because it's been pouring with rain for the last 3 months, you can't grow anything there. Similarly, if the rain's not coming at the right time, you can't grow anything. And it's as simple as that. So I think the interesting thing, and this is really sort of starting to move into where we are now and starting to look into the future, is how can you really understand the story behind the weeds, story behind the actions and the structure and the growth of the crops? How can you use a much more subtle and flexible methodology to be able to get to grips with how crops grow? And coming back to the core point of this presentation, this all comes down to location, and it all comes down to the precision that's required using RTK GNSS to be able to do that. So again, sort of harking back to my OS days, the favorite phrase within the company and what nearly became the slogan of the company was "Everything happens somewhere." And I think that the key in the agriculture space is that there are parts of a field which are unproductive. It's not always clear why they're unproductive. It's not always visible why they are producing slightly lower yields. It's not always necessarily visible why there are more weeds there or they're more prevalent to grow. Yes, it might be more seeds in the ground, but what else is going on there? And also in some places, crops just naturally seem to suffer from more disease. They are maybe less, they have less accessibility to nutrients because of the soil type, or those nutrients are just less present in that particular soil. But you do get patches of fields where disease just seems to happen more often. And being able to understand that and understand that location is really, really critical to precision farming. And as I'll sort of describe the progression in a minute, this understanding is not really about picking out one piece of information. It's not really about having a precision view of one layer, whether that's sort of weeds or nutrient application or soil type, but it is multimodal. It's the interplay of these things which allow you to really get to the grips of what's happening in the field. My previous company was called Small Robot Company, and we were using sort of robotics and AI to develop a per plant farming system. And the hypothesis behind that was really that if you can understand each plant in the field, then you can truly care for the field. So if you can really see how plants are emerging, are they coming up from seed? Are they doing well? Are they planted where they're expected? Are they struggling with things like rocks, like it's clearly a problem in this field? Then you can really get a grip into what's going on in the field. And in particular, with a focus on how you fertilize and provide nutrients for those crops and how you control weeds. And one of the things we found most fascinating when we started, and our starting point was just to understand where the plants were. We started to get these maps back that didn't show that sort of uniform view that I was talking about before, with this standard sort of 200 or 300 plants per meter squared of wheat growing up in the field. You have these strange inconsistencies, these gaps, these areas where plants don't grow. And you also get areas where plants seem to be doubled up. And growing far too close together, which from a farming term is almost as bad, because when you have those plants growing close together, they don't grow very well. The root systems don't have the space to be able to expand properly. And what tends to end up happening is you get plants, but not an awful lot of crop or yield out of the top of it. So this allowed us to be able to see that if you just could use those variable rate or sectional or sort of nozzle control sprayers that Kit was talking about, but feed them with the information of where the plants actually were, then you could just spray the fertilizer where the crops are and not on the mud. Because it seems slightly insane to say it, but up to 30% of fertilizer is just sprayed on mud. It has no purpose, it serves no benefit for the crop, and all it does is pollute the field and pollute the watercourses. And then when you start to build this up into layers, you can start to understand more what the impact of different factors are within a field. So when we started to sort of delve into where the value was for what Small Robot Company did, we found that because of the detail of the imagery that we were collecting in the field, we could differentiate between early stage wheat and a really nasty weed called blackgrass. Now, blackgrass is nasty for all sorts of reasons. It grows and takes over sort of parts of the field. It spreads a huge amounts of seeds and outcompetes the wheat plants. It's becoming largely resistant to herbicides. And when it sort of starts happening in a field, it's quite often very hard to tell you've got blackgrass until you get to later on in the season, when the darkening of the plant, hence its name, shows where it is. And then the impact of blackgrass became really, really obvious for us when we started working with farmers, when we mapped blackgrass very early in the season, and then saw what the impact that had on the yield later on in the season. And so combining these two maps together allowed us to really understand the impact and start to provide a value on what that early stage detection was for farmers. But ultimately, there's only so much you can get from just mapping where the plants are. There's only so much you can get from understanding the location. So how can we move this forward? Now, this is really, I suppose, the sort of hypothesis I wanted to throw out there at the moment, primarily because I'm not allowed to talk about what I'm working on at the moment until the start of next month, so I wasn't really able to delve into this anymore. But I wanted to talk about the idea of URNs, of universal resource numbers. These are ultimately the location of things, and they're used in mapping, in navigation, to be able to define location, to define the context and the meaning of location. And I think that the way that data is being collected at the moment, using sort of existing systems, and use particularly with sort of more advanced farmers, using sort of novel systems for being able to understand the soil, being able to understand the growth and the performance of their crops, being able to understand where the weeds are, being able to understand the topography, all of these layers build up. And I think that what the next step in this process is to understand, when you have these layers in place, when you can understand the soil and the crop, and when you understand the topography of the field, where you understand where the weeds come up, where you understand how nutrient is being absorbed in certain places, and when you can start to understand the sort of the flow of weather, although obviously that's changing a lot as we go on, then you can start to really understand the potential of a field, and you can understand what you can do to maximize that potential without relying on what's happening in the field right now. And if you can apply that with precision at field scale, then you can start to produce a system which is far more flexible in terms of delivery of the crop and yields that a farmer expects, and start to understand how to redeploy or reuse a field in a way that is best suited for the soil and the environment that it's in. And so what I wanted to do really, I suppose, was suggest that we need to start thinking about this multimodal view of a field. We need to start thinking about plugging in all this data together and applying clever tricks around AI, etc., to build that understanding. So then we can start treating the field as the sort of complex, layered environment that it is, and understand that the crop is only one part of this, and just treating the crop and just thinking about the way you maximize a crop is a very narrow approach to maximizing the opportunities for agriculture as we move forward. Thank you.
Thank you so much, Ben. My goodness, you've really presented us the holy grail there, I would say. But that's something interesting about agriculture. I mean, in manufacturing, for example, you know what your maximum capacity is in any time frame, and we don't really understand that at this point, and that's really what we're missing. Yes, I completely agree with your vision of the future there. I've already got a few questions. I was going to take my own privilege and ask one first, really cheekily. But if you want to put some more questions in there, I'm going to jump to them actually because they've already started. But if you want to do it on camera, you can put your hand up and we can do it that way. So if I invite Kit and Alex back as well, I'm going to fire them out to whoever wants to pick them up. So is anybody including what an automated system can see and not just where it knows via the RTK GPS? So it can avoid driving over crops. And I would also say things like soil sensors and stuff, if we're using more of them, we don't want to squash them. Any thoughts?
So, I mean, I'm sure Kit's got a lot to say on this as well, but from our perspective, a small robot company, when we started, we were buying those cheap rubbish GPSs because we couldn't afford anything else. So we had to do an awful lot of work using odometry to understand where the robot was in the field, and particularly because it was really light. So, you know, tractors are fantastic in that they can just crush through things, you know, sort of many tons of iron sort of going through. Whereas we had a unit that weighed between 200 and 300 kilos, with a ground pressure of, you know, significantly less than your foot. So it had a tendency to slide around all over the place as well. So being able to counter that using odometry and using sort of visual indicators for row following was extremely important. That was my little view. I'm sure Kit will pick up and now let's pick up bigger view.
Yeah, well, all I'll say is absolutely yes. I mean, certainly if you take environments where GPS occlusion is a real issue, then camera sort of guidance, as it were, is really prevalent. So there are lots of companies building robotics for driving through vineyards and orchards and that sort of thing, and they have a heavy use on cameras. What I always say, yes, I guess slightly to counter Ben there, is I always say that if you're working in an open field agriculture, GNSS will always be the linchpin of your navigation, as far as I'm concerned, because ultimately there's sometimes not a lot to look at. If I'm driving down a field rolling it, like as in literally just with a set of rolls that firms down the soil with a robot tractor, there's no margin to see. It's not as though we've just turned the soil from yellow to brown, or we've mowed a crop from this tool to this tool. There's nothing to see. It's just a flat area. So GNSS in an open field environment for me is always king and key. But yeah, there's plenty of environments where cameras for navigation is highly important. That doesn't mean that we won't use cameras for other things like safety and all those stuff.
Want to add anything to that? Yeah, Alex.
Not too much. I think you guys pretty much covered it. I think the only caveat I would throw in as well is with LiDAR cameras, you will suffer from environmental conditions. In England, when it rains all the time, LiDAR is iffy. And then obviously on a foggy day, you will have problems as well. So it comes down to that reliability where GNSS will be the same, the same in the farm, as long as things don't change and you don't block your view of the sky, things will be reliable in that sense.
And it's about merging that stuff. So the favorite techie phrase at SRC was reverse Kalman filters, combining the odometry and the GPS and the cameras information to be able to try and squish together some sort of understanding of where you are to a relatively high level.
Yeah, and just to jump back in, like if you look at my covered examples, GNSS isn't going to be working great, and you need to think about what PNT source it comes in. How do you complement it? Obviously, if you've got a robot that has a camera in, you'll try and use it, but you need to always think about what PNT source is, the pros and cons to it in those scenarios.
I guess that comes all the way back around to the reliability we talked about earlier from that circle. I'm going to jump to Lauren to give her a question. She's got a good one. So what do you think are the key barriers to widespread adoption of precision agriculture across Europe? Is it about affordability? Do you think there's a certain level of tech avoidance due to limited connectivity or capability gaps in rural EU regions? I should say the short answer is yes to all. And Harper do a lot of work on this, so I might pass to Kit.
Yeah, I mean, my personal view on it is mostly business case. I think there's often a view of farmers that it's a life choice or it's a way of life and all that sort of stuff. But actually, you go and talk to farmers, most of them brass tacks counts. And the problem with a lot of precision ag is lack of business case. And that's because agriculture is a complicated system, as Ben's just explained to us. And I can do something this year and get one yield, and I'll do the same thing next year and get another yield. Well, if the year after I adopt some precision ag, I'll get a different yield again. Guess what? But did it have anything to do with the thing I did? Did it have anything to do with the precision ag? And did the precision ag I do pay for itself or save enough money that it paid for itself or whatever? So business case and financial viability is what is always lacking. And that is why the adoption of auto steer and auto section control has been successful compared to a lot of other things, because it's very clear from day one. By having auto steer on my tractor, at the end of the day, I'm less fatigued. So that's not a financial benefit, but it's a personal benefit. I'm less fatigued when I have an auto steer tractor. It becomes a clear financial benefit when you realize that I've just put less fertilizer on that field because I've got auto steer. And farmers talk and they tell people that, and they go, I got this auto section, I've saved 10% of fertilizer this year. I really struggle to find any academic reference for that 10% saving, but you go and talk to farmers and they say it all the time. I save 10% by having section control, and they know because they know what they buy every year. So clear business cases, when they're there, they're adopted. When they're not, they don't. So an example of that, sorry, just keep rambling on, is like yield maps. Yield maps, as I said in my talk, have been on combines since the mid-90s. They've been available. A lot of people have got them. A lot of people have got 20 years of yield maps. Do they ever actually look at them or do much related to them? No, a lot of the time they just sit on a shelf or sit on a memory stick and don't really add much value. So because people aren't sure what they can do with that information. So business cases is so important.
And they're not granular enough. I mean, coming back to your point about the barcode, right? And the fact that, headers are getting wider, which means actually they're getting less granular, which is insane. Yeah, completely. You have to sort of accurately show that there is a saving that they will have. And it can be time, and it can be, sort of physical well-being and stuff like that. But there needs to be something there. There is, I think, also though, a huge barrier around just sort of attitudinal stuff too. I think that maybe both Kit and I, in our previous incarnations, had suffered from a view, particularly in cereal farmers, that, oh well, it's small. Why would we use small? You know, we got big, you know, and big's great. And that is, you know, it really is an attitudinal thing, particularly when you're looking at sort of autonomous vehicles, because yes, they cannot be unreliable to a certain extent, although things have got a lot better. But you know, the reality is that there isn't a huge amount of difference applying multiple. You know, if you're already bought into the autonomy, to have one big and multiple small, it doesn't really stack up to have big machinery. And that is very much, and if you go to, you know, any of the big farm shows and you see the farmers sort of getting super excited over their coffee, sort of staring at the latest green or red piece of machinery, then it's got very little to do with whether that's an effective piece of kit in the field. It's much more, it's got really nice shiny bits on it.
Yeah, I mean, to be honest, is a brilliant question, Lauren, and I could probably talk about it for the next hour. It's a complicated answer, but I'll put some links in the follow-up if you want to do some further reading on it, because there's a lot of really interesting stuff around it. So I'm going to add this final comment from Graham, which is a bit technical, so I hope someone understands it. Are you familiar with the work of ISO TC 347, which is data-driven agri-food systems? Apparently might be relevant to you, Ben.
Aware of it, we were part of the process of putting it together.
There you go.
So, well, I wasn't. It was the CTO at the time, but yes, it's very much so.
Brilliant, thank you. I'm just aware we're up against time, which is annoying because I have 100 more questions. Is there any final thoughts or questions or anything anyone wants to add? Well, I'll wrap it up there. Well, oh, I've gone then, Graham.
Well, I'm just going to jump in on that. So it's good that Ben knows. Maybe everybody else should know. So ISO TC 347 dragged itself up out of the morass of thinking about everything to do with smart farming a few years ago, and the Smart Farming Strategic Advisory Group laying its monster egg of a report, and has then ground through trying to make sense of what's missing in the way of standards to join all the pieces up. What have you not already got in terms of ISO standards that help you interoperate and move data around and connect systems and join up the data ecosystem in the way that it relates to farming? Personally, I don't care if you can join one tool to one thing that you've created. I'm interested in how you can do it more generally, and that's where ISO TC 347 is trying to work. If you want to find out more, there's a whole load of webinars on YouTube. There's material on LinkedIn if that's where you want to go. There's the BSI Mirror Committee, AGE 34. If you think you'd like to find out more, you can find that via an obvious set of searches. If you want to ask me, ask me. But I'm really keen that people very active in this sort of community find out more about it and help steer it in the right direction to support particularly UK farming, or more broadly the agri-tech sector in Europe and beyond. Thank you.
Brilliant, thank you. And I may well follow you up on that, because that is something we talk about day in, day out, interoperability. I could whole nother webinar in that.
Super, thanks, Becky.
So I'm just going to say a quick roundup then. Thank you so much to our three speakers. You've been absolutely brilliant, and I think you fitted together really well. Just really, really, really helpful. I've learned a lot. And thank you also to the Royal Institute of Navigation for helping. Lucy's just commented in there for helping put it together, because we couldn't do it without Rin. As I said, we'll send a follow-up with some links in, some further reading based on some of the comments and questions. I'll try and drop a few bits in there for you. If there's anything I've missed, let me know and I'll add it in. And I was just going to highlight three very quick things to you. So one is we'll send a link to sign up if you want to find out about future meets events. We'll only email a couple of times a year. It's not going to be spammy, I promise. But if you want to hear about them, then you can sign up for those. We have a day-long program once a year, which is agriculture for innovators. So if you are new to agriculture, you can join us for the day. Christina's put the link in there. We'll be hearing from people like DEFRA around policy. We'll look at funding. We'll hear from some farmers and how they work day to day. So it's a nice program that we've run since 2019. So if you're interested in learning more about agriculture, I would recommend that one. And finally, the other thing to mention is there's quite a lot of funding opportunities around at the moment. So if this has really whet your appetite and you're like, oh, maybe we could do something in agriculture, there's a nice little program, for example, from DEFRA called the Adopt program, and it's all about trying new stuff on farming in farms. there's other funding calls. We'll expect to see more later this year. But the long story short is, if you're interested, there may well be some funds that we could help point you in the direction of if you want to do a bit more. But otherwise, I know I've run over a little bit, so I will just say thank you so much, everyone. Any feedback would be welcome as our first in the series. And thank you again to Lucy and our speakers today. Thank you, Graham. That's brilliant. I'll ping that round. Thank you. Cheers. Have a good afternoon, everyone.
Thank you. Bye-bye.
Thanks so much, Ben. Cheers.